Alright, so picture this. It's June 26, 1897. Spithead, off the coast of Portsmouth, England. The entire British Royal Navy is lined up for inspection. 165 warships stretching 25 miles across the water. Queens, princes, foreign dignitaries, lords of the Admiralty, everyone who's anyone in the British Empire is watching. This is Queen Victoria's Diamond Jubilee Naval Review, the grandest display of naval power the world has ever seen. Britain showing off, making a statement. We rule the waves. We are untouchable. And then, cutting through the centre of this perfectly arranged fleet, unauthorised, uninvited, moving faster than anything anyone's ever seen on water, comes this sleek, narrow boat. 100 feet long, barely 9 feet wide, spewing smoke, leaving a massive wake. And absolutely embarrassing every single warship in the Royal Navy. The boat's name? Turbinia. The man at the helm? Charles Algernon Parsons. And what he's about to do in the next 15 minutes will change naval warfare, marine transportation and power generation forever. But to understand why this moment matters, you need to understand who Charles Parsons was and why he built this boat in the first place. Charles Algernon Parsons was born in 1854 into about as much privilege as you could have in Victorian England. His father was William Parsons, the 3rd Earl of Ross, a serious astronomer who built the largest telescope in the world at their family estate, Birr Castle in Ireland. The family was intellectual aristocracy, the kind that actually used their wealth for scientific advancement rather than just sitting around collecting rents. Young Charles grew up surrounded by science, engineering, precision instruments, and the resources to experiment with anything he wanted. His childhood home had workshops, laboratories, and some of the finest scientific equipment in the British Isles. But here's what's interesting. Most aristocrats' sons became politicians or military officers. They managed estates, sat in Parliament, maybe dabbled in science as a hobby. Charles wanted to build things, actually build them with his hands, not theoretically, not as a gentleman observer. He wanted to get covered in machine oil and metal shavings. His family, to their credit, supported this. They understood that engineering was becoming the future. He went to Trinity College Dublin first, then to Cambridge, studied mathematics, graduated with first-class honours in 1877, and then he did something unusual for an earl's son. He became an apprentice, not a gentleman engineer overseeing things from a distance, an actual hands-on apprentice at Armstrong's Engineering Works in Newcastle, one of the premier engineering firms in Britain. He worked in the shops, learned machining, learned how to operate lathes and planers, got his hands dirty, understood how things were actually built, not just how they should theoretically work. Then he moved to Kitson's in Leeds, worked on torpedo development, rocket-powered torpedoes actually, which were experimental and frankly kind of dangerous, but Parsons learned about propulsion, about moving through water, about converting power into thrust, all things that would become crucial later. By 1884, Parsons was working for Clark Chapman and Company, heading up their electrical equipment development, and this is where things get interesting. Because Parsons had been thinking about a problem that was holding back the entire electrical power industry: steam engines. See, in the 1880s, if you wanted to generate electricity, you needed a steam engine to turn a dynamo. But steam engines of that era were reciprocating engines, pistons moving back and forth, converting that back and forth motion into rotary motion through crankshafts and flywheels. They worked, but they were inefficient, vibrated like crazy, and had physical limitations on how fast they could run. And speed mattered, because electrical generators worked better at higher speeds. Parsons looked at this and thought, why are we converting steam pressure into back and forth motion, then converting that back into rotary motion? Why not just make the steam create rotary motion directly? The idea wasn't entirely new. People had experimented with steam turbines before, but previous designs had massive problems. They tried to extract all the steam's energy in one stage, which meant the turbine blades had to spin at insane speeds, sometimes over 30,000 revolutions per minute. Materials couldn't handle it. Turbines would literally tear themselves apart. Parsons's breakthrough was the multi-stage compound turbine. Instead of one stage extracting all the energy, he used multiple stages. The steam would expand through the first set of blades, lose some pressure, expand through the second set, lose more pressure through the curl, third set, and so on. Each stage extracted a little bit of energy, and the turbine blades only had to spin at manageable speeds. The genius was in the details. He designed each stage with slightly larger blades than the previous one because the steam expanded as it lost pressure. Bigger volume, bigger blades. The staging meant each set of blades operated at optimal efficiency for that particular pressure. And because the steam was gradually slowed down rather than all at once, there was almost no vibration. Reciprocating engines shook buildings. Parsons' turbines ran so smoothly you could balance a coin on edge while they operated. In 1884 he built his first prototype. 7.5 kilowatts of power, 18,000 revolutions per minute. Smooth, efficient, no vibration. It worked. But getting from proof of concept to commercial product required solving dozens of practical problems. How do you lubricate bearings spinning that fast? How do you seal the steam without leaking? How do you control the speed when electrical load changes suddenly? Parsons worked through each problem methodically. He designed automatic governors that adjusted steam flow based on electrical demand. He created special bearing designs that could handle high speeds. He figured out thrust bearings to handle the axial forces from the steam pushing through the turbine. Every solution created new questions, but Parsons had patience, resources, and absolute conviction that turbines were the future. He patented it, set up his own company in 1889, C.A. Parsons and Company, and started building turbines for electrical generation. By 1890, the world's first power station using turbogenerators opened at Forth Banks in Newcastle. Parsons' turbines were generating electricity, proving that this technology wasn't just theoretical, it was practical, it was reliable, it was the future. But Parsons had another vision: marine propulsion. Think about it. Ships in the 1890s used reciprocating steam engines too. Big, heavy, slow-turning engines that took up massive amounts of space and had the same efficiency problems as land-based engines. What if you could put a steam turbine in a ship? What if you could make ships faster, more efficient, smoother? Naval architects and shipbuilders thought Parsons was crazy. Turbines spin too fast, they said. You can't connect a turbine directly to a propeller. The propeller would spin so fast it would just thrash the water into foam and provide no thrust. The physics don't work. It's impossible. Parsons didn't care what they said. In 1893, he founded the Parsons Marine Steam Turbine Company, and in 1894 he commissioned the construction of an experimental vessel, Turbinia, built by Brown and Hood at Wallsend on Tyne, 103 feet long, 9 feet wide, incredibly narrow, incredibly light, built for speed. The design was radical. Most ships had broad hulls for stability. Turbinia was like a racing shell, narrow enough that you almost couldn't walk past someone coming the other way. The hull was steel, light but strong. The boiler was specially designed, water tube type, could generate steam at higher pressures than typical marine boilers. Everything about the ship was purpose-built for one thing: speed. The first trials were disappointing. Turbinia could barely hit 20 knots. Parsons had been right about one thing: the turbine worked beautifully. Smooth, powerful, no vibration. The engine room crew could have a conversation in normal voices while the turbine was running. Try that on a reciprocating engine ship and you'd go deaf from the noise. But the skeptics had also been right about something. The propeller was a problem. Parsons initially used a single propeller on a single shaft. Big mistake. The turbine spun the shaft at about 2,200 revolutions per minute. Way too fast for a propeller. The blades just churned the water into foam. The ship vibrated, the thrust was terrible, and the speed was mediocre. This is where Parsons showed what separated him from ordinary engineers: obsessive determination. He didn't accept failure. He experimented. He built a testing tank specifically to study propeller behavior, one of the first cavitation tunnels ever constructed. He tested different propeller designs, different blade shapes, different pitches. He photographed the water flow, he measured thrust, he systematically worked through the problem, and he discovered the problem: cavitation. When the propeller spun too fast, it created areas of low pressure behind the blades. The pressure dropped so low that the water literally boiled, even at normal temperatures. Vapor bubbles formed, then collapsed violently as they moved into higher pressure areas. This cavitation destroyed thrust, damaged the propeller blades, and made the whole system inefficient. You could actually hear it, a harsh, rattling sound as thousands of tiny bubbles imploded against the metal. The solution wasn't slowing down the turbine. That would defeat the whole purpose. The solution was distributing the power, so Parsons redesigned everything. Instead of one turbine driving one shaft with one propeller, he installed 3 separate turbines: high pressure, intermediate pressure, and low pressure, arranged in series so the steam expanded through all 3. Each turbine drove its own shaft, and each shaft carried not one propeller, but 3 propellers. 9 propellers total. This distributed the power, reduced the load on each individual propeller, lowered the tip speed, eliminated cavitation. In trials in April 1897, Turbinia hit 34.5 knots. 34.5 knots. The fastest ship in the world at that time could maybe manage 27 knots. Turbinia was 7 knots faster than anything afloat, faster than any destroyer, faster than any cruiser, faster than any warship anywhere. Parsons had proven it worked, but he had a problem. Nobody cared. He'd presented his results to the Institution of Naval Architects, showed them the data, explained the technology, demonstrated the efficiency gains. They were skeptical. Some were openly dismissive. "This is interesting, Mr. Parsons, but we'll stick with proven technology, thank you very much." The Admiralty, the Royal Navy's procurement department, showed polite interest and did absolutely nothing. Parsons was frustrated. He'd revolutionized power generation on land. His turbines were generating electricity all over Britain. But nobody would give marine turbines a chance. He needed to make them pay attention. He needed a demonstration they couldn't ignore, which brings us back to June 26, 1897, the Diamond Jubilee Naval Review. Every important naval person in the world would be there. Every warship Britain had would be on display. Press from every country would be watching. It was perfect. Parsons loaded Turbinia onto a railway car, transported her to the coast, assembled a crew and waited. The review started. Ships lined up in perfect formation. Battleships, cruisers, destroyers, torpedo boats arranged in precise rows. The Prince of Wales inspected the fleet. Foreign dignitaries admired Britain's naval might. Bands played, flags flew. Everything was proceeding according to plan, ceremonial, formal, impressive. And then Turbinia appeared. She came tearing through the lines of warships at full speed. 34 knots. A rooster tail of water behind her wake spreading out in a massive V, rocking smaller boats, black smoke pouring from her single funnel, the turbines screaming. Parsons himself was in the engine room monitoring steam pressure, adjusting controls. The crew on deck was waving, absolutely loving this. And every officer in the Royal Navy was absolutely furious. Officers on the bigger ships watched through binoculars, trying to identify this unauthorized vessel. Signalmen tried to flag her down. "Stop immediately, identify yourself." Turbinia ignored them all. She had a job to do, make an impression. The Admiralty sent patrol boats to intercept her. Steam launchers, the fastest small craft available. Couldn't catch her, not even close. Turbinia just circled around them, faster, more maneuverable, leaving them wallowing in her wake, looking foolish. She raced between the lines of battleships, past destroyers that were supposed to be fast, past cruisers, past every ship present, and not one of them could touch her. The gap wasn't small. It was enormous. She was making the entire Royal Navy look obsolete. It was unauthorized. It was outrageous. It was brilliant. The crowd on the warships was shocked, then amazed, then cheering. Prince Henry of Prussia, the Kaiser's brother, watched from a German warship and immediately understood the implications. Foreign naval attaches took notes. Journalists scribbled furiously. Parsons had just demonstrated, in front of the entire world, that British naval technology was obsolete. Now, there are different accounts of whether this was actually unauthorized, or whether Parsons had gotten quiet permission from someone in the Admiralty who wanted to see what Turbinia could do. Some say the Admiral of the fleet specifically asked Parsons to demonstrate the boat. Others say it was completely rogue. The truth probably lies somewhere in between. Parsons was well connected. He'd been working with the Admiralty for years. Someone probably gave him a wink and a nod. But officially, unauthorized, disruptive, spectacular. Within days, the Admiralty was in contact with Parsons. Within months, they were ordering turbine-powered destroyers. HMS Viper and HMS Cobra were commissioned in 1899, both using Parsons turbines. They were the fastest destroyers in the world. Viper hit 37 knots in trials, 37 knots. Nothing else came close. These weren't experimental boats anymore. These were frontline warships built to Admiralty specifications, ready for combat. Both ships were lost in accidents in 1901. Viper ran aground in heavy fog off the Channel Islands. Cobra broke apart in heavy seas in the North Sea, her hull splitting in two, likely due to structural weaknesses in the design, not the turbines. The losses were tragic. 58 men died on Cobra alone, and they slowed adoption temporarily. Critics said the turbines made the ships too fast, too fragile, too experimental. But the Admiralty had seen enough. The technology worked. The losses were about hull design and navigation, not propulsion. In 1906, HMS Dreadnought launched, the first all-big-gun battleship and the first battleship powered by steam turbines. Dreadnought could make 21 knots, faster than any battleship afloat. She made every other battleship in the world obsolete overnight. Britain started building dreadnoughts. Germany started building dreadnoughts. The United States started building dreadnoughts. The naval arms race that would lead to World War I was underway, and it was powered by Parsons turbines. But it wasn't just warships. Commercial shipping adopted turbines too. In 1901, the Clyde steamer King Edward became the first turbine-powered passenger ship. In 1905, the transatlantic liners Victorian and Virginian entered service with turbines. Then came the big ones. Mauretania and Lusitania in 1907, both turbine-powered, both capable of over 25 knots, both holders of the blue riband for fastest Atlantic crossing. And yes, Titanic, launched in 1911, turbine-powered. The turbines weren't why she sank, obviously, but they were part of what made her fast enough to maintain schedule on the North Atlantic run. By 1910, steam turbines had essentially replaced reciprocating engines in all new large ships. Faster, more efficient, smoother, more reliable. Parsons had changed marine propulsion forever. But here's the thing. Marine turbines, as revolutionary as they were, weren't even Parsons' biggest impact. His real legacy was electricity generation. Remember that first turbine in 1884, 7.5 kilowatts? Enough to power maybe 100 light bulbs. By 1895, Parsons had built 100 kilowatt turbines for Cambridge. By 1899, he'd built a 1 megawatt turbine for Elberfeld in Germany. 1,000 kilowatts, more than 100 times larger than his first design. By 1922, 50 megawatt turbines, 50,000 kilowatts. The generating capacity had increased 10,000 times in Parsons' own lifetime. 10,000 times, same basic technology, just scaled up through relentless engineering improvement. And turbines didn't just get bigger, they got better, more efficient, more reliable, more economical. The first turbines were maybe 2% efficient. By the 1920s, they were pushing 12%. Still not great by modern standards, but vastly better than reciprocating engines, which rarely exceeded 5% efficiency. By the early 1900s, Parsons turbines were generating the majority of the world's electricity. Not just in Britain, Germany, France, the United States, everywhere. If you turned on an electric light in 1910, chances were overwhelming that the electricity came from a Parsons turbine or a turbine built on his patents. Here's what makes this even more remarkable. Parsons' fundamental insight, that continuous rotary motion is more efficient than reciprocating motion, that steam should expand through multiple stages, that turbines are the right way to convert thermal energy into mechanical energy, those principles still dominate power generation today. Think about it. Coal-fired power plants, steam turbines. Nuclear power plants, steam turbines. They're not using nuclear reactions to turn generators directly. They're using nuclear reactions to heat water, create steam, run it through turbines. Same basic principle Parsons established in 1884. Natural gas combined cycle plants, gas turbines, which work on similar principles, plus steam turbines using waste heat. Geothermal plants, steam turbines. Even some solar thermal plants, steam turbines. Current estimates suggest approximately 60% of all electricity generated globally comes from steam turbines operating on principles Parsons established over 140 years ago. 60%. That's coal, nuclear, natural gas, geothermal, concentrated solar. All turbines. All descendants of that original 1884 design. The reciprocating steam engine, which had dominated power generation for over a century, which had driven the Industrial Revolution, which had seemed like the pinnacle of engineering achievement, was completely obsolete within 20 years of Parsons' invention. That's how superior turbines were. Parsons himself didn't stop innovating. He worked on geared turbines to improve efficiency. He experimented with optical instruments, partnering with telescope manufacturers. He even tried to create synthetic diamonds, applying extreme heat and pressure to carbon. That one didn't quite work out, but the fact that he tried shows his mindset. Always experimenting, always pushing boundaries. He was elected Fellow of the Royal Society in 1898, knighted in 1911, made a member of the Order of Merit in 1927, won basically every engineering award that existed. The Franklin Medal, the Faraday Medal, the Copley Medal, recognition from around the world. But beyond the awards, beyond the honours, Parsons had fundamentally changed how the world worked. Transportation, turbines, power generation, turbines, naval warfare, turbines, industry, turbines, his companies, C.A. Parsons and Company and Parsons Marine Steam Turbine Company, continued growing. Parsons turbines powered most major British warships through both world wars. They powered ocean liners. They powered generators in power stations worldwide. The companies themselves went through various mergers and acquisitions over the decades. The Marine Steam Turbine Company eventually became part of what's now the BMT Group. C.A. Parsons merged with other firms, became part of Northern Engineering Industries, then Rolls-Royce, then was sold to Siemens in the late 1990s. But the technology, the fundamental innovations, those persisted. Parsons died in 1931 at age 76, while on a cruise aboard a ship powered by turbines he'd designed. There's something fitting about that. Poetic, even. He spent his career revolutionizing ships, and he died aboard one of them, still travelling, still moving forward. Turbinia herself had an interesting afterlife. After her demonstration at Spithead, Parsons kept using her for experiments and demonstrations. She visited Paris for the 1900 exposition. She was nearly destroyed in 1907 when another ship being launched lost control and almost cut her in half. She was repaired, used occasionally, then retired. In 1926, the Science Museum in London wanted her, but they didn't have space for the whole ship, so they cut her in half. The aft section, with the engines and propellers, went to the Science Museum. The forward section went to Newcastle and was displayed in Exhibition Park. In 1961, using a reconstructed centre section, Turbinia was reassembled and displayed at Newcastle's Municipal Museum of Science and Industry, which later became the Discovery Museum. She sits there today, restored to her 1897 appearance, the only surviving example of the ship type that changed the world. You can visit her, walk around her, see those 9 propellers that solved the cavitation problem. Look at the turbines that made her the fastest ship in the world. Stand next to the hull and imagine what it must have been like on June 26, 1897, tearing through the Royal Navy at speeds nobody thought possible. So, what's Parsons' real legacy? What did he actually accomplish? He took an idea that everyone said wouldn't work and made it work. He took skepticism and turned it into inevitability. He took a technology that naval architects dismissed and made it the standard for every major ship built afterward. He took power generation that was limited, inefficient, and held back by physical constraints and made it scalable, efficient, and capable of powering modern civilization. Most inventions improve things incrementally. Parsons' turbine was discontinuous. It wasn't 10% better or 20% better. It was fundamentally different, orders of magnitude superior. When something is that much better, adoption becomes inevitable. You can resist it, you can be skeptical, you can stick with familiar technology. But eventually, reality forces change. The British Navy could have ignored Turbinia. They could have dismissed Parsons as a showman, censured him for disrupting their review, gone back to reciprocating engines. But they couldn't ignore 34 knots. They couldn't ignore ships that were 7 knots faster than anything they had. They couldn't ignore technology that made their entire fleet obsolete. So they adapted. They adopted. They built turbine-powered ships. And, within a decade, steam turbines had completely replaced reciprocating engines in naval vessels. Not because someone forced them to, because the technology was undeniably, obviously, overwhelmingly better. That's the thing about truly revolutionary technology. It doesn't need committees or mandates or regulations to succeed. It just needs to work. Demonstrably, measurably, undeniably work. And once it does, adoption is just a matter of time. Parsons proved his technology worked in the most dramatic, public, undeniable way possible. He embarrassed the Royal Navy in front of the world, and rather than resenting him for it, the Navy thanked him, ordered his turbines, and change naval warfare forever. 127 years later, we're still using his technology, still generating most of the world's electricity with steam turbines, still building ships with turbines, though now gas turbines in many cases, based on similar rotary principles, still benefiting from the fundamental insight that continuous rotary motion is more efficient than reciprocating motion. Every time you turn on a light, there's a decent chance a steam turbine somewhere is generating that electricity using principles Parsons established. Every time you see a naval vessel, large commercial ship, jet aircraft, or modern power plant, there's probably a turbine in there somewhere, descendant of Parsons's work. That's impact. That's real legacy. That's what it means to actually change the world in fundamental and lasting ways. Not bad for a guy who just wanted to build a faster boat.